This part will be fitted to my solar powered CNC mill that I'm converting and will act as a heatsink for an 1800 watt brushless DC motor. Designed in a Libra design, this heatsink will form part of the spindle drive and mount to the spindle belt housing. It also has an acrylic window to see the brushless outrunner and provides a mount for a rotary encoder for accurate motor control too. This AMT 102 capacitive rotary encoder provides up to 8,192 counts per revolution and up to 7,500 RPM and should allow for precision control for machine tapping. I hope to run the new motor at around 6,000 RPM, so well within the scope of this rotary encoder. The motor is not fixed at the base or heatsink, but attached to the spindle belt housing via 4 screws, which will require heatsink compound on both the motor and heatsink mounting points to use the spindle belt housing as an additional heatsink. The belt is a HTD tooth type that's lightly tensioned around 2 40 teeth timing pulleys. I chose this size as there are more teeth in contact with the pulleys and the belt will run slower with less load, so should last quite well. There are 2 identical motor heatsinks to make, the other for the Z-axis, although this could be milled faster with the spindle speed upgrade, where the Z-axis has a belt reduction of 4:1, similar to the X and Y axes, although may need a heatsink due to lifting the weight of the spindle components. As mentioned before, this mill runs purely on solar power, with a 50 watt solar panel and a set of 12 volt batteries that used to have around 75 ampere hour of capacity, although now with all the upgrades I'll need some heavier duty batteries and a larger solar panel, so I have 2 12 volt 240 ampere hour batteries ready and a 330 watt solar panel. I just need to wire it all up. The X and Y axes run on 12 volts, where the Z axis and spindle will run on 24 volts and will hopefully look something like this. So, I like to use a Libra design for the CAD, computer aided design model, and Fusion 360 for the CAM element, being computer aided manufacturing. Essentially, creating the G-code for the mill to run. But first, the toolpaths need creating around the part, and Fusion 360 has some great tools for this, and is easy to see the route the tool will take prior to cutting through stock. The first cutter will be an 8mm end mill with a small corner radius that will remove the bulk of the material layer by layer. The only issue with my mill at the moment is the lack of CNC Z-axis, so I'll have to lift and lower the Z-axis manually for each layer. So these Z-axis movements will have to be removed manually in the G-code to keep the machine at the same height during each layer. Where there are height changes between each layer, I've programmed this into the mill to pause milling and tell me the required height so that I can manually move it, then continue the operation. And then once the bulk of the material has been removed, it's onto the 4mm long tool to cut out all the features. This will probably take some time as the cutter is long and more flexible, so I'll have to take shallower cuts at 2000 RPM, and that's the maximum speed for the current motor that's on there. It took a while to sort the toolpaths out, as I'm only just getting to grips with the Fusion 360 system, although there are plenty of tutorials online. I may even make one of my own. So down in the depths of the toolpath, you can see the starting position and the layer drop down points that I'll have to manually move. To set up the toolpath to allow for manual Z-axis movement, I'll need to set it up to only have one layer and then restart the same G-code for each layer, rather than multiple layers. So this operation has created intermediate Z-axis movements that will need to be amended. So I just need to generate or pass the G-code, then check the toolpaths at the points where it will raise and lower to see how it interacts with the part. Then adjust the G-code to keep the machine on the same level. That way the machine will do one layer at a time while I get on and do something else. Then it's a case of putting the G-code on a micro SD card and putting the file on the mill's microcontroller. In this case it's a Tinsy 4.1 microprocessor running an Arduino sketch I wrote on the Arduino platform. You can take a look at the code from the link in the description or from my website. So this microprocessor not only interprets the G-code to control the O-drive motor controllers, it also sends all the drawing commands to the game Arduino Dazzler board to display everything on the HDMI monitor and allow me to control the machine a lot easier and see what's happening. I thought it best to do a test pattern first on paper just because I'm constantly developing the microprocessor code to make it easier and safer to control the machine. Plus I don't want to crash any milling bits. One of the features of the display is to show the movement of the table. To be fair, this was just me getting fancy with the game Arduino. Again, I'll leave a link for this in the description. This sounds a bit like Indy 500 from the Atari 2600, if you're as old as me and remember that. Another handy device, rather than me standing around in a cold garage, is this mag mount reversing camera that I use on the MGF trailer, a 2.4 GHz transmitter and a 12V monitor. This allows me to watch the progress of the mill and just pop out to lower the Z-axis during each layer. Right, now to mill the part. First of all, after mounting the vise, I'll need to check that it's square to the machine. Then set the front left of the stock as the datum point using this edge finder. So it just needs the kick on the Y-axis, then the X-axis, and then cancel out the radius of the edge finder in both X and Y. I just thought I'd go over a quick test to see if everything's running okay. And then drop 1mm at a time. I know this milling cutter won't be able to do the full depth, so I've ordered a longer cutter. This is performing really well, especially with the diaphragm air blower that's keeping all those chips away too. Now to try the 4mm cutter to see how it performs and if I need to adjust the speed. That seems very capable. Although that wasn't supposed to happen. I forgot to raise the Z-axis. Oh well, the cutter still works, although it's a bit shorter. After much milling, the chips are looking good and building up fast, especially with the new long 8mm cutter that's just arrived. I was thinking of putting a datum point on this display just so I can see where it is in relation to that. That's something I'll have to set up later though. Then it's over to the 4mm cutter again to machine out the external heatsink fins and internal features. These internal features are designed to create turbulent air to remove more of the heat. We shall see. And also I made the gaps between the fins to be 4.2mm, so there's good clearance for the 4mm bit, especially being that long. And that's the main feature finished, alongside another blank ready for the Z-axis. Just the underside to do now. You can see a slight step on the side of the hole at the back there. This is due to the backlash being slightly off. I've since updated the code to easily measure and set up backlash for X and Y axis, so this won't be an issue in the future. So now it's just a case of drilling and tapping the mounting holes, although I'll tap the holes off the machine, as I'm not quite there with machine tapping yet. I think this has turned out quite well apart from the damage from snapping a cutter. Still, it won't affect anything, luckily. I hope you enjoyed this one. Well, I'll be making the spindle belt housing next, and that will be the largest part I'll make on this machine so far. But there will be plenty more to see after that. Well, I hope to see you in the next video.